Greetings and welcome to Chapter 5, where we will be talking about integrals, and I'm going to be using the PowerPoint slides that were provided to accompany Stewart's Calculus Early Transcendentals 8th edition. And in the first section of Chapter 5, we're going to talk about areas and distances. This section has a lot of slides, and the topics that are in here, there's really one primary topic. It's very detail oriented and it's very attainable, but I just don't have the desire to spend as much time on certain details as others. So I might just fling my way through a number of these slides. Some of them I'm going to be mumbling them under my breath and say, skip that, don't worry about it. Others I'm going to sort of look at them and say, yeah, let's really zero in on this part. Let's target this. Let's actually work this part out. So we're kind of going with the flow on this one, which is maybe not my typical style, but this is a slightly unusual section, but it's an important section. Conceptually, in the study of calculus, it's definitely an important topic, so I don't want you to think that this is what we're looking at in this section is trivial at all. So you'll see what I mean as we go along. In this first example, we're talking about finding an estimate for the area under just a portion of the parabola y equals x squared. And you'll notice on the x-axis, we're only going from 0 to 1. This point that's up here has an x-coordinate of 1, and in order to find the y-coordinate of that point, we took this x value of 1, we plugged it into the equation, we squared it, we got out the corresponding y value of 1, and there it is. Now here, you know that, and you could have figured that out, and you knew that it had a y-coordinate of 1. But as you work with other functions, and actually as we take this blue region that's labeled S right here, and we chop it up into smaller pieces, we're going to have some additional y values, and we'll calculate those y values by taking x values and plugging them into that equation. So what's being illustrated here is sort of that chopping it up idea. Stewart is saying here that we're taking the region S and we're dividing it into 4 strips, and those are being numbered 1, 2, 3, and 4. And important to notice that along the x-axis, the total, maybe interval, we'll call it from 0 to 1, has been chopped up into these 4 strips, and it takes 5 points to create 4 horizontal intervals here. The x-coordinate here is 0 at the beginning of our interval, so that's the first one, and then the second x value, third x value, fourth, and fifth. So it's 4 strips defined by 5 x values, let's say. And we're going to be using all 5 of those, but sometimes only 4 of them at a time. And I'll show you what I mean. If we used, well, we'll get there. Okay, so here we are approximating the area of each strip, and then we're going to add up all of those approximations in order to get an approximation of the area under the curve. And when I say the area under the curve, I mean between the parabola and the x-axis. And since we're only looking at it from 0 to 1, it ends up being this area that's contained by my 3 red, they were supposed to be lines, but they're not lines. I don't do lines. Just don't have a steady enough hand. All right, so we're approximating the area under the curve. And we can do that by, let me zoom back in actually. we'll take these 5x values that we have by taking the interval from 0 to 1 and chopping it up as we were just talking about. And what I'm going to do is I'm going to take the second x value, not this one. We're going to let that one go for a moment. We're only going to look at 1, 2, 3, 4 x values. So these 4 x values. And I'm going to take the first one, which is 1/4. Let me say that again. I'm actually going to call this the 0th x value. This will be the first x value. This will be the second and the third and the fourth. And we'll talk about why we're doing that also. So I'm going to take this first x value, and I want to know how tall this rectangle is that, zoomed in as far as I could, that starts at the x-axis and it goes up to my curve, and then that rectangle is going to the left over to my 0th x value, which just so happens to be 0. In order to find the area of that rectangle, I know how wide it is. Right, it has a width of 1/4, but how tall is it? Well, it's the height of the rectangle is whatever the y value is when x equals 1/4. So the y value, or we could just write down the coordinates of this point. We see that the x coordinate is 1/4, and the y coordinate can be determined by taking your x value and plugging it into your function. 1/4, comma, f of 1/4. Similarly, this point has an x coordinate of 1/2, and you could find its y coordinate, in other words, the height of this rectangle, by taking the x value and plugging it into the function, f of 1/2. Notice also that the width of each one of these rectangles is the same. So we created these 4 strips so that they have equal width, which is nice. It's going to simplify things for us a little bit. All right, so the author is saying, notice, I said that we're gonna skip over this 0th x value, and we were going to use the 1/4 in order to determine the height of that first rectangle. That's what the author is going to refer to as right endpoints. So if you're using the x coordinate that's on the right-hand side of a rectangle in order to determine that rectangle's height, then you're using right endpoints. Not only did we use 1/4 as the right endpoint, since it was the right endpoint of that rectangle, I then drew the top of the rectangle to the left, came back down, and then there's the rectangle for which we're going to find the area. And as we said, each rectangle has width 1/4. And the heights, we said we were going to take those x coordinates, plug them into our function, which is the x squared function, in order to generate the corresponding y values. A little bit of notation, since we're using right endpoints and we cut it up into 4 rectangles or 4 strips, we're going to call that capital R for right sub 4. The area of each one of those rectangles is found by taking the width, which I'm going to call delta x, and multiplying it by the height, which is, if this is not the 0th x coordinate, but if it's the first x coordinate, I'm going to say that this is f of x sub 1. Our function in this problem is the x squared function, which is why that first x coordinate is getting squared. We've got delta x again here, the width of the next rectangle. And what's the height of that rectangle? Well, we determine that by taking our second x coordinate, x sub 2, which happens to be 1/2, plugging it into our function, which requires us to square it. We get the y value. We multiply that by the x value, and we've got the area of that rectangle. And so on. We have to do that 4 times in order to find the area of the 4 rectangles. We add up all those areas. We get 15 30-seconds, and then there's that fraction expressed as a decimal. Notice, however, and we're going to see this in another graph, another illustration, all of these rectangles stick up above the curve. And when we add up all of these rectangles, what we're getting is an overestimate. Okay? So, an overestimate of the actual area under the curve. So the real area, capital A, of area S is less than R sub 4. Instead of using right endpoints, which is what happened in the scenario that we just worked through, we could use left endpoints, and that's going to be capital L sub 4. We're using the left, let's say the left x coordinate of each rectangle in order to determine the height of the rectangle. I wouldn't normally do this, but I think it's going to be helpful. Let's look at this rectangle first. Let's look at this one. The left-hand x coordinate for that rectangle is 3/4. And how do I determine well, we already know, that the width of that rectangle is delta x. So we could do this, or we could, if you've redrawn this diagram, or if you have access to these notes and you want to be printing them out and diagramming right on there, we could say that the width of that rectangle is delta x. We also know that in this problem, delta x is equal to 1/4. But how do I find the height of that rectangle? Because I'm defining these rectangles using their left endpoints, I would use this x value of 3/4. I would plug that into my function and find that this height, and I am drawing it there on purpose instead of putting it out here because I'm not working with the right-hand edge of this rectangle. I'm looking at the left-hand edge of it. That height right there is f of 3/4. So the area of that rectangle would be delta x times f of 3/4, which is 1/4 times, it turns out to be 9/16. Okay, so that is that particular rectangle. Then we could go in and we could look at this rectangle. This one also has a width of delta x, and it has a height of f of 1/2. And then this rectangle right here has a width also of delta x. And I don't think I can zoom in. Oh, that's pretty far. It has a height of f of 1/4, right? Because we're using that left endpoint, that left x coordinate. And then there's another rectangle. It's right here. You can't see it, but it's there. It has a width of delta x, and it has a height of f of 0. But our function is the squaring function, so it's 0 squared, which is 0. So that rectangle has a height of 0. That's why I didn't want to do that one first. Okay, better that we started on the right. But normally, if not exclusively, you will progress your way through the calculation of the area of this rectangle, this rectangle, this rectangle, and this rectangle from left to right. I did it from right to left just so that we could encounter this 0 rectangle last. Notice that each of these rectangles is under the curve, below the curve. So in terms of trying to calculate the area under the curve, we've excluded this area. And we have excluded this one, and we have not taken this into account. We haven't taken that into account either. So this is an underestimate. So it turns out that the L sub 4 is an underestimate, So the area will be greater than, and after doing all the calculations, it turned out that L sub 4 was equal to approximately that decimal. The area under the curve is actually greater than that under approximation, and the area is still less than this over approximation or overestimate. If instead of using 4 strips, we used more, like, what do we have here, 8 strips, you can see that there's less wasted space, okay, less unaccounted for space. So this is going to be a more accurate estimate. It's still an underestimate, and this one is still an overestimate, but it's not as far over. Imagine we cut this thing into 2 strips. 1, 2, 3, 4, and here's 1/2. We would have to come up to here and then draw our rectangle over to here, and then we would be using this as the area of our first rectangle, and then this would be our second rectangle. Look at this, that's a gross overestimate. Okay, we're including a lot of area up here that's not supposed to be included, not to mention these areas. So the more strips we cut these intervals into, the more accurate an approximation we're getting. So there's your capital A value, your estimated area. Well, your actual area is now between 2 values that are closer together. So it's a more accurate estimate. And these n values that we're seeing in this table go along with left approximations and right approximations, where the n determines the number of rectangles or slices that we're using, and these 2 values are not nearly as close to each other as these 2 values, which are not nearly as close to each other as these 2 values. All right, so again, the more slices, the more accurate the estimate, whether it's an over or an underestimate. And you can read the actual text that's on that slide if you want. I think it was on the screen long enough. You can pause it, check it out. Here it's really easy to see the overestimations that are occurring, that are sticking up above the curve. But if we use, that's for 10 slices or 10 rectangles. But if we do 50 rectangles, you almost can't see the overestimation that's happening there, or over approximation. The other thing that's being mentioned right here is that right endpoints produce upper sums, in other words, overestimates, because this function is increasing. This as an x coordinate takes us up to this point as a y coordinate, and since we're using right endpoints, it's taking us over to the left there, which causes us to take an overestimate in the area of this rectangle. Notice that a portion of that rectangle sticks up above the curve. When you're using right endpoints and you're applying them to a curve that's increasing, and y equals x squared is definitely an increasing function when you start at 0 and move to the right. Look at it getting taller and taller and taller. Okay. Right endpoint approximations will produce overestimates. Left endpoint approximations will produce underestimates when you're working with an increasing function. If we were to cut this region into infinitely many slices, it would turn out, as we keep compressing the overestimate and the underestimate closer and closer to each other, as the number of slices heads out toward infinity, whether you're working with the right estimate or the right points or the left endpoints, as you take that limit as send n out toward infinity and you've got infinitely many slices, you end up with a very distinct clean area under the curve. So the actual area under that curve, x squared, from 0 to 1 is 1/3. And there are certainly other curves which are more complicated, where it's decreasing to this point, and then it's increasing to this point, and then it's decreasing again to this point, and you could be using your right estimates or your left estimates, and in some cases on part of this it's going to be an overestimate, underestimate, under, and then you're back to over. It's all going to come out in the wash, because eventually we're going to make those segments so narrow that the margin, overestimate, underestimate, isn't even going to matter. The way in which, just a little expression here, a little formula, this is a good one to have in order to calculate the width of each strip. The author is calling them here, which is fine. The width of each strip can be calculated by taking the upper and lower bounds of your interval, finding their difference, and then dividing by the number of strips you're going to be creating, and that will equal the width of each strip, delta x. And we'll see that delta x repeatedly, so that's a good one to have. N subintervals. Earlier I was talking about the x coordinates under this graph that we were working with, right? Y equals x squared, and this had an x coordinate of 1, and then we cut that into these 4 subintervals, and this was 1/4, and this was 1/2, and this was 3/4, and the x coordinate here, of course, is 0, and I said let's call this the 0th x coordinate, and we'll call this one the first x coordinate, and 1/2 would be the second x coordinate. I called that one, I have to be careful with my language I'm using here, I called this one, I'm scribbling my arrow down here, the 0th x coordinate, because I knew that we were going to be doing this, using this term x sub 0. And the last one, the nth one, x sub n, is going to be the x coordinate of your right boundary on your interval. And x sub 0 is the left endpoint of your interval. All right, so we're cutting it up into all these intervals. Yep, that looks good. Here are some little formulas just to get an idea of how we're getting out to those various x coordinates that are defining our subintervals. Let's look at x sub 2. If we call this x coordinate A, and this x coordinate is B, literally A equals 0, B equals 1, we're cutting it up into 4 slices. If I start at the beginning, at my A value, and then I add 2 rectangle widths to delta x's, then I would move from A over 1 delta x over 2 delta x's, and I would be here at x sub 2, my second x value. Second x value, first x value, 0th x value. It's weird, admittedly. Scroll, please. There we go. Scrolling. What you're seeing here, I don't love the top of this slide, but the bottom half of this slide, or bottom 2/3 of this slide, is good. Everything that you're seeing, here I like. This is notation for that right estimate, where we're using the x coordinates that go along with the right hand edge, vertical edge, so to speak, of the rectangle. We know that the width of each one of these rectangles is delta x. We know that when we're using right estimates, that if we're focusing on this rectangle that goes from A over to x sub 1, that the height of that rectangle is f of x sub 1. And we can find the area of that rectangle by taking delta x in the horizontal direction and multiplying it by, in this case, f of x sub 1. And that's what you're seeing at the bottom of the screen right now. That's the area of the first rectangle. And then the second rectangle has a different height, potentially. And the third one, and the fourth one, and so on, all the way up to the last rectangle, the nth rectangle, which is going to have a height of f of x sub n. And we still have to multiply that by the width of that rectangle, which is delta x. So some slightly more specific and yet general still it's not an explanation, but a formula or description for finding the right estimate area under a curve. Another illustration of the fact that as we use more strips, the approximated area under the curve becomes more accurate. In the original slides, this 2 was not here, so I inserted that because it is referenced as equation 2. I think the author thought that this 2 was sufficient to cover it, but I didn't think it was enough, at least not for me, but I'm a little slow. So the area of the region S that lies under the curve of gravity. Right, so let's just look at the difference between these two formulas. We're still calculating the area under the curve, so there's our capital A. We're still, well, not still, we haven't been talking about this for very long, but this idea that we're going to be creating infinitely many strips in order to have a hyper accurate estimation, and when you do actually take the limit as n goes to infinity, then we get an exact value for the area under the curve, and we're applying those ideas to the right estimate and the left estimate. So conceptually, you're familiar with what's going on in these two equations so far, and then the right estimate is all of the stuff that's inside of these square brackets. And the left estimate is what's inside of these square brackets. And okay, so now let's examine what's in those square brackets. The right estimate starts out with an x value, an x coordinate of x sub 1. In the left estimate, the first x coordinate that we're using is the 0th one, x sub 0. I don't love that. I don't like my little diagram there. So really that's the primary difference, is the x coordinate that we're using in order to find the height of the first rectangle and then each subsequent rectangle. All right, so x sub 0, where's the best place for me to show you this? Not there, not there. Should I go backwards? I'm going backwards. Just in case, for a little bit of additional clarification. Some of you aren't going to need this. I'm going way back. Perfect, here it is. In the right-hand estimate, we're using this x coordinate. That's x sub 1. The height of that rectangle is f of x sub 1. Remember that the height of this rectangle, not as good in green as it was in red, the height of this rectangle is defined by f of x sub 0. And the left-hand edge of this rectangle was defined by f of x sub 1, x sub 2, x sub 3, And again, the leftmost rectangle, which in this diagram is not much of a rectangle, the height of this rectangle right here is again determined by f of not 0. It's not f of 0. It's f of x sub 0. All right, how many times can I say it before I just start driving you bananas and you're ready to get out of here? And then visually, for sure, there's the difference in the last term. There's a difference in all the terms in between also, but when you're doing a right estimate, you will use your last available x coordinate, which when you're on the interval from a to b, this is going to be b. This x coordinate right here is b minus delta x, because it's the left edge of the rightmost rectangle. The x coordinate of the left edge of the rightmost rectangle is b minus delta x. In person, it's so much nicer to talk about this stuff because I can read the classroom and I can answer questions on the fly, and we can draw more diagrams if we need to. So that's why I'm being a little bit repetitive here and trying to reference different diagrams, because I don't know how many of you are still struggling with what it is that I'm talking about. So I try to keep hitting it from different angles, but we'll keep moving. This slide is interesting. I don't think I ever did this when I learned calculus, but admittedly at this point, that was a while ago now. We're not using a left endpoint or a right endpoint. You can see that the height of this first rectangle, the height of it is being determined, like, look here, here's the top of it, at the top of this dashed line, x sub 1 with an asterisk on it. Why are we choosing that as the x coordinate to plug into our function to generate the height of our rectangle? What we're being told is that instead of using left or right endpoints, we could take the height of the ith rectangle to be the value of f at any number in that interval for that rectangle. And the author is calling these x sub 1 star, x sub 2 star as sample points. Okay, I'm not familiar with that. I understand that still helps me find the area of a rectangle. The width of it is still delta x, except the height of it is now f of x sub 1 star. Okay. As long as I cut my area under the curve into enough rectangles, those rectangles are going to be so skinny that if you want to use the left edge, the right edge, or some kind of an x value that's between those, it's not going to matter. You're still going to get the correct area. But that won't happen until you apply the limit as your number of rectangles goes to infinity. What else is going on in the area problem? Yeah, super. You can read that. We talked about this already. The right endpoints produce an upper sum or an overestimate if your function is increasing. Left endpoints produce a lower sum or an underestimate if your function is increasing. This is an interesting depiction. Here we're choosing those x sub I star values as x coordinates to plug into our function to generate y values, which are the heights of the rectangles, except we're strategically picking those so that the y value that we generate is the minimum, or if you want to find the absolute lower estimate, or rather upper estimate, you could try to maximize that y value by choosing a very specific x coordinate on that interval. Is there a good interval in here for me to talk about that? Yeah, I guess it's this second one. I'm going to just talk about this rectangle for a second, and maybe more specifically we'll talk about this interval right here. And let's call this x sub 1, and this x coordinate will be x sub 2, and this x coordinate will be x sub, I don't like this at all, so, I don't know, sub 1 star. If we used the left endpoint, I'm only talking about this interval now. If we use the left endpoint, which is x sub 1, to calculate the height of the rectangle, I'm looking at x sub 1 as an x coordinate, and this point right here, which is actually on the blue curve, has coordinates x sub 1, comma, f of x sub 1. All right, so that's how we would find the height if we were using the left edge method. If we wanted to use the right approximation, so we're still working with the same rectangle, the same interval, except I'm going to use the x coordinate that's at the right-hand side of that interval. And I could plug it into my function, and it would give me the y coordinate of this point. So I could then draw that over to here and find the area, and that would be my approximate area. So initially, when I used x sub 1 as my x coordinate, it put me up here on the curve, and I could draw over and down, and I would get this as my approximate area. When I used the right-hand edge, this point gave me a y coordinate, which caused me to draw the top of my rectangle there, which gave me this rectangle. It's beautiful, I know. Oh, it's kind of Christmassy. That's nice. It gives me that red rectangle as my approximate area for the area under the curve. I think you can still see it in there. Both of those estimates are overestimates. Where's my curve? Do I have blue? I need blue. There we go. So the green is an overestimate, the red is an overestimate, but the black one that I drew is an underestimate. How am I supposed to get my hands on a point that has this as a y coordinate? Well, I would need this x sub 1 star to be my x coordinate. It's the x coordinate on this interval that gives me the lowest possible y value on that interval, which would give me the most extreme underestimate for my area under the curve. It keeps the entire rectangle under the curve, for that matter. It doesn't protrude partially up into the curve. Excuse me, it doesn't take me all the way maximally for the biggest overestimate possible. It's the most extreme lower estimate. If I applied that on all these little subintervals for all of my rectangles, then I would have the most extreme lower sum or under approximation for the area under this curve. Why in the world would you want to do that? I'm quite sure that there are applied problems where you would want to know your most extreme underestimate and your most extreme overestimate. I don't know, the first thing that comes to mind is if you were building a very large building, a hospital or something maybe, you would want to know the underestimate of the amount of concrete that you need to bring with you, which tells you the fewest number of cement trucks maybe that you would have to have drive out there on a daily basis. And you would want to calculate the most extreme overestimate of the amount of concrete that you're going to need to use. It's not the best example. But if I'm bidding on the job and I know that the number of concrete trucks, cement trucks that I have to send out to the job, I don't even own as many cement trucks as would be required at the lowest approximation, I probably shouldn't even bid on the job because there could be a lawsuit, or my contract might cause me to have to pay extra because I wasn't able to deliver fast enough or something like that. I'm sure we could think of other examples where it would be very beneficial to know a lowest, most extreme underestimate and overestimate. But that's all I had at the moment. So far we've been talking about adding up areas, and a lot of them, sometimes infinitely many of them, as we take the limit as n goes to infinity. Adding up all of those rectangles, I think summation notation, which we talked about last chapter, would be very beneficial to use. And here is a sort of generic statement using sigma notation to find the, this is actually for the right approximation. And yeah, if we look at this equation right here, since we're taking the limit and sending n to infinity, that's going to give us the actual area under the curve. But without that limit, you'll notice that the index is starting at 1, and here this says x sub I, so your first x coordinate that you would be working with would be x sub 1, which means you've skipped over x sub 0, which means we're definitely working with right approximations. We're using the right-hand edge of all of those rectangles in order to calculate the height of those rectangles. In the second statement, this is the left approximation. We're still using an index that's starting at 1, but the first x coordinate that we end up using is x sub 1 minus 1, in other words, x sub 0, in other words, lowercase a, in other words, the left edge of all of our rectangles. Or we could do that thing where x sub I star puts us somewhere on the interval for each one of the strips. This is a true statement. Maybe I skipped over the slide where this was utilized. This is definitely a shortcut formula for finding the sum of a finite number of squares, right? 1 squared plus 2 squared plus 3 squared plus 4 squared all the way up to n squared. Instead of adding up all of those squares, you can shortcut it by using the right-hand side of this statement. And then there's another little subsection, which is an applied topic for what we've been talking about, and it's called the distance problem. And we know that distance is equal to rate times time, or velocity times time. And I think I'm going to start out immediately by looking at a rectangle. That's my curve, right? We were looking at a portion of a parabola previously. There, that's my curve this time. Just this little part of a blue line. And if my line segment up there is coming over 2 units, and maybe it's at a height of 60, and I've labeled my horizontal axis T, I'm going to label my vertical axis V, and if I wanted to find the area under this curve, which seems strange, I would need to find, well, this would be really easy. All I have to do is find the area of a rectangle. And I know how wide my rectangle is. It's 2. and I know how tall it is. It has a height of 60, so the area under the curve is 120. 120 what? Well, length times width. Let's look at our units. What if t is measured in hours and velocity is measured in miles per hour? Well, then I've got a width of 2 hours times a height of 60 miles per hour. Can I cancel these units, these hours? And I end up with 120. Oh, there are units left. It's miles. Of course it is, because we just did velocity times time, or time times velocity, and what does that equal? It equals distance. So we've ended up with an answer that's 120 miles. In other words, if we're finding the area under a curve, and here's the curve again, we're finding the area under a curve that's on a coordinate plane where the horizontal axis is representing time and the vertical one is representing velocity, then the area under the curve will represent distance. That's what this entire little subsection is about within 5.1. So here it is. You're seeing a table that has times on a 30-second car trip, or 30 seconds worth of a car trip, the velocities at some various sort of time markers along the 30-second interval, 0 seconds into the interval, 5 seconds in, 10 seconds in, and then we're being told it's probably going to make more sense to convert from miles per hour to feet per second, because time here is being measured in seconds. So in order to have our units match up better and be able to cancel stuff out, let's make the conversion. 1 mile per hour equals 5,280 feet per 3,600 seconds. There are 5,280 feet in a mile. There are 3,600 seconds in an hour. If we graphed this, how wide would this first strip be that goes from 0 seconds to 5 seconds? I think it would have a width of 5. And how wide would this one be? From 5 to 10, also 5. And another 5, and another 5. Okay, so delta x is equal to 5. Great. And then we have our y values, 25, 31, 35, and so on. Don't forget, though, this first time value, 0, is x sub 0, and 5 is x sub 1. So if you were asked to calculate a right approximation, or the right-hand sum, or however it's phrased, make sure that you're using the correct x values and then the corresponding correct y values in order to generate the correct areas of your rectangles, because then you're going to add them all up in order to find your total distance traveled. During the first 5 seconds, the velocity doesn't change very much, so we can estimate the distance traveled using the time, that time, and assuming the velocity is constant. I personally don't agree with that. 25 feet per second, 31 feet per second. I don't know if those are, I guess those are close to each other. They're not as close to each other as 47 and 45, or 45 and 41, but yeah, well, 6 seconds apart, whatever. Let's call it 25. So 25 times 5 makes 125 feet. We've used this is a left approximation, right? We've used the left-hand edge of that rectangle. We're using the y value that goes along with x sub 0. And that y value of 25, we're using that as the height of the rectangle. And that's on the left-hand side of this rectangle. And then we can march forward and use the other left-hand edges of those rectangles. Remember that this was f of x sub 0 was the 25. And then here's f of x sub 1, f of x sub 2, all of our delta x's, all of the 5s, those are all the same. That's good. And then we're adding up the area of all those rectangles, and we come up with 1,130 feet traveled over the course of those 30 seconds. Instead of starting out by using f of x sub 0, which was the 25, we could have said, 25, 31, those are the same. Not really, but let's just pretend. So instead, let's start out by using that y value of 31. And remember that that's actually f of x sub 1. And we're going all the way up to f of x sub n, which in this case is x sub 6, which is our last y value, the right-hand edge of the rightmost rectangle. And this is the height of the right-hand side of our leftmost rectangle. Sounds like insanity, doesn't it? So much nicer when you have a graph to go along with it. Well, honestly, if you want a graph to go along with it, where'd it go? You could plot these points, 0, 25, 5, 31, 10, 35. You could plot those as points. You could even draw a rough curve that passes through those points. Grab a piece of graph paper and scale it. If you're struggling with this conceptually and it would be better for you to see it, it wouldn't take very long to plot that. It's got to be 30 units wide. So on your graph paper, have each horizontal square represent 2.5 maybe, so that you're 2 blocks wide for every 5 seconds. And then vertically, you're going up to 41, so pretend you're going up to maybe have vertically each square represent 4. Or vertically each square represent 5. Oh, that's a lot easier to count by 5s than to count by 4s. You'll only have to go up a little bit more than 8 squares, 9 squares. Somewhere between 9 and 10 squares is the number 47. So it's not going to be a gigantic graph on a piece of graph paper. Velocity, time is going from A to B. T sub 0 is equal to A. That's your 0th x coordinate, but now it's a t coordinate. Your last t coordinate is B. That's the right-hand end of your interval. We're calling that t sub n. That's your very last t value or x coordinate. Delta x has now become delta t because our horizontal axis is representing time. Here's your left approximation because we're starting out using the leftmost t coordinate or x coordinate, right? So that's as far left on the interval as it goes. This second equation that you're seeing is your right approximation because we're actually using our second t coordinate or x coordinate, right? X sub 0 was the first one, or t sub 0 was the first one. Down here, t sub 1 is actually your second x coordinate. And your total distance over that time span or time interval, whether you're using the left approximation or the right approximation, if you're taking the limit and you're sending n, your number of strips, to infinity, they will end up being equal to each other. Your two approximations will be equal to each other. Wow. So that is the end of our slides. We're already at the 54-ish minute mark in this video. It's a little rough, I understand. Let me toggle over into WebAssign, which is what I use with my students, to look at a couple of homework problems. I'm not actually going to write these out because I think that we just clobbered this topic conceptually, and you know how to draw rectangles, and if you hear me say a right approximation versus left approximation one more time, you might scream. Okay? So in part A, in this question, we want to estimate the area under the graph of, in this problem, the function is f of x equals 3 times the square root of x. In our horizontal axis, we're going from 0 to 4, and we're going to cut this thing into 4 rectangles. So we now want to find, using 4 approximating rectangles and right endpoints, which is why we're seeing I can't draw on my screen anymore. I'll use my cursor just as a pointer. We're calling it R sub 4. So it's a right approximation where we're using right endpoints. If we're using right endpoints, then the first x coordinate I want to look at is not x sub 0, it's x sub 1. Our interval's going from 0 to 4. What's 4 minus 0? What's 4 divided by 4? So what's delta x? Okay, so the width of each interval, of each rectangle, is 1. We're starting at 0. 0 is x sub 0. This, however, 1 is going to be x sub 1. I come over to x sub 1, and then I need f of x sub 1. That's going to give me a y value. And visually, I can see that I would come up and this would be the y value that goes along with my x coordinate. Now, if I'm using right endpoints to draw my rectangles, what I should do now is I should draw a rectangle from here. This is the right edge of my rectangle. This is the correct height of that rectangle. I should now be drawing over to here and then down again. So this is not the right diagram. This looks correct. This is x sub 1. I come up to the appropriate y coordinate, and then I go left because I'm using right endpoints. So I'm along the right-hand side of my rectangle, and then I go left from there. Oh, I have to scroll down here. Now that we've chosen that as our correct graph, would you say that that's an overestimate or an underestimate? Well, my rectangles are sticking up above my curve, so that is going to be an overestimate. So repeating the process, but using left endpoints. If I'm using left endpoints, then my first x coordinate that I'm going to use is going to be x sub 0. X sub 0 is the a value. The a value in this case is 0, and our b value is 4. So x sub 0 is my a value, which is 0. If I'm using left endpoints, again, the first x coordinate that I'm going to use is x sub 0, which is a, which in this case is an x coordinate of 0. From there, with that x value in mind, I need f of x sub 0. So in this problem, I need f of 0, which means I need the square root of 0 in this problem. I actually need 3 times the square root of 0, which is 0. The width of my rectangle is still delta x. The width of my rectangle is still 1. But the height of this first rectangle is going to be f of 0, which is 0. This rectangle right here does not have a height of 0. Look farther down. This rectangle does not have a height of 0. This is in my way. This rectangle does not have a height of 0. My iPad is picking up my voice and it's transmitting it and showing me how loud I am. However, this first rectangle does have a height of 0. I was distracted by this readout down here. So this is a contender. Okay, this is a possibility, as is the one above it, because that first rectangle has a height of 0. This one right here. And we're using left endpoints. So let's go over to our next rectangle. Using the x coordinate of x sub 1, I find the corresponding y value. It's here. I'm using left endpoints, so I have to draw to the right. in order to create my rectangle, and then down again. This one looks pretty good. The one below it is identical. Now let's come here. I'm using x sub 2 as my next left endpoint. Corresponding y value, 3 times the square root of 2, brings me up to here. I draw my rectangle to the right because I'm using left endpoints. That rectangle looks correct. Let's see what's going on with the other graph down here that was a contender. There it is, x sub 2. I need f of x sub 2. That's 3 times the square root of 2. That's good. Oh wait, I should have stopped right here. Why is this coming all the way up to here? It looks like they're using some kind of a midpoint between x sub 2 and x sub 3 for some reason. I don't know why they're using that as an x coordinate and ending up with this as a y coordinate. Strange. This is not right. It is possible to do an approximation of an area under the curve by using midpoints of your sub-intervals. So you would use 0.5 and 1.5 and 2.5 and 3.5 as your x-coordinates. You'd find the corresponding y-coordinates, and those y-coordinates would be the heights of your rectangle or rectangles. But that's not what we're doing here. That's very weird. So it turns out that this is indeed the correct answer. Left endpoints, drawing our rectangles off to the right. All of those rectangles were under the curve, and so that is an underestimate. Notice that we used left endpoints on a function that's increasing, and that gave us an underestimate. And then this question asks us to evaluate the Riemann sum. What in the world is a Riemann sum? Oh, thanks. It took me all the way back to the beginning. That's a Riemann sum like written out. The Riemann sum is more typically written using sigma notation. So something that looks more like, did I just blow right by it? Not really. You know what I'm looking for though. I'm just trying to make your head spin by scrolling through all of these slides again. Here we go. I would call this a Riemann sum. Riemann, I forget Riemann's first name. Shame on me. Well, Riemann was a person, was a guy, and he came up with the idea of using all of these rectangles in order to find the approximate and then ultimately the exact area under a curve. And so the sum, this idea of adding all of these up, well, this thing, but look, I mean, it's a sum, right? So this is the Riemann sum. And what this question is asking us to do is to essentially find, not essentially, it's asking us to find the left endpoint approximate area under this curve. Since you're doing left endpoints, you're going to need, you need a couple of key ingredients for this. You need to know delta x. Delta x is going to be found by taking b, which is 14, minus a, which is 2. That's going to give you 12. You'll take the 12 and you'll divide it by n, which in this problem is 6. So the width of each of your rectangles is going to be 12 over 6, which is 2. So delta x is 2. This is a left endpoint approximation, which means the height of each rectangle will be calculated using the x-coordinate that goes along with the left-hand edge of each rectangle. You could figure out what this graph looks like if you wanted to, but I'll tell you that the height of your first rectangle is going to be f of x sub 0. So that very first x-coordinate. which is this one. X sub 0 is always your A value. The height of your next rectangle will be f of x sub 1. X sub 1 will be 2 units to the right of x sub 0, because delta x, the horizontal difference that we're stepping forward with, the width of each rectangle was 2. So again, the height of your second rectangle is f of x sub 1, which is 2, it's f of x sub 1. What's x sub 1? It's 2 units bigger than x sub 0. It's 4, right? Because our first x sub 0 was 2, and then delta x is 2, so we got to move to the right 2 units, and that's our new x coordinate, which means the y coordinate is f of that new x coordinate, f of 4, and then f of 6, f of 8, f of 10, f of 12, 2, 4, 6, 8, 10, 12, that's 6. That's 6 left edges. You're not using the 14. You're not using x sub 6. If we were doing a right endpoint approximation, you would end up using that one, but you wouldn't be using x sub 0. But in a left endpoint approximation, you'll use x sub 0 through x sub 5. 0, 1, 2, 3, 4, 5. That's 6 values, 6 rectangles. I think you got it from there. This is actually an assignment that includes problems from the next section, so we'll probably be glancing at this exact example somewhere during the next video. Thanks for hanging with me on this one. I know that was tedious and I was very repetitive, but this is a very important topic, and the Riemann sum, I'm glad that the homework assignment included Riemann's name. Go do a little look. Just go in and look up Riemann sum, and you'll see some illustrations immediately that will remind you of the lesson that we just talked our way through, and you'll find out Riemann's first name. Maybe you could learn some other stuff about Riemann. Smart guy. Smart like you. See you next time. Thanks.